In this video, I'm going to be showing the design of a step-down buck regulator. Over the past couple years, several manufacturers, including TI and Analog Devices, have come out with these new ultra-low EMI step-down converters, and I wanted to give one of them a try. So for this video, we're going to be walking through a design using this LMQ61460Q1. It's a TI part. It has some pretty cool features. If you go look at the data sheet, it's got some integrated capacitors inside the package that they advertise as being really low EMI. So we're going to create a design using KiCad for this and then get that design built and test this out. So the first thing I like to do for something like this is to take a look at the data sheet and go find the example schematic for this. What I'll do then is take this into KiCad and we'll just put that down without any component values, and then we can go through the data sheet and fill in all the component values. So here in the application section of the data sheet, we can see they've got an example schematic here. So we're just going to go over to KiCad, drop down all these parts to copy this over, and then we can go through the application section and the specs in the data sheet and fill in all the component values. Okay, so now that we're in KiCad, I've got a blank schematic here, and we're just going to start adding symbols. So the first thing we need to do is add some connectors so that we can get the power in and out of this. And for that, I'm going to use some banana jacks, and so those will just be single pin connectors that we'll place on the board later. So we can go into connector. We need just a 1x1 connector here, and drop that down. We'll rotate that, so this will be our power in. And then we're going to duplicate that so we have power ground on each side. So this will be our input side, and then on the output side we'll have the same thing. We'll have power out and the ground for that. And then we want to hook these up. So on the ground I want to hook up those, so I'll just go here, search GND, grab a ground pin, and we'll just hook that and duplicate it over here and connect the wire. Next on the schematic, to start out, I want to place the regulator component. Unfortunately, this part is not available in KiCad standard libraries, so we need to build it ourselves. Going to the data sheet here has the pin table and the pinout for it. So we're going to go back to KiCad and open up the symbol editor. So we've got the symbol editor open. Now KiCad comes with all these libraries already in it. I've got the list shortened down somewhat. We want to actually create a new library to put this in, because we don't want to save our parts inside the built-in ones that come with KiCad. So we're going to go to new library. We can make this a global one, which means it shows up in all of our projects, or we can make it a project one, which means it'll just be accessible from this project. So for this, I want this to just be accessible in this project. You can always change that later. So I've got my project folder here, and I'll just go make this as a regulator. So now we've got our new regulators library here, and we're going to create a new symbol. And we'll name this, it's the LMQ61460-Q1. We don't want to derive from any existing symbol. All the defaults here should be just fine. So now that we've got this, we need to add some pins. So there's a couple ways to do this. One is there's the pin table, and then you can also just individually add pins. This one's pretty straightforward, so we're just going to individually add pins. So we grab the new pin tool. The other thing I always like to make sure is that my pins always land on a 50 mil grid. So we're going to change our grid settings, and then we'll start up here. And so the first pin is the bias pin. Pin 1, and for now we're just going to not worry about the electrical type. You can do some rule checking and stuff for that in KiCad, but it doesn't really matter for this simple schematic, so we'll just leave those all alone. And so we'll place that over here, go down to PVC. So I find it easier to just go create all the pins, and I can double check them, make sure they all match what the datasheet says. You really don't want to get this wrong. And then after I've got the whole list created, then I'll go back to their example schematic and rearrange them in a way that makes sense. So we can see from their schematic here, they've got a particular way of arranging them that's not necessarily in the numerical order, and this helps make the schematic look a lot more clean. So we're going to rearrange ours so that they look similar to this, so that our schematic looks the same as theirs. So now that we got the pins roughly laid out, we can go create a box around them that'll serve as our component boundary. We'll go place the reference designator and the symbol name. And then we'll put the anchor so that it sits roughly at the center of the component. Now we can save that and close out of this. So now back in our schematic view, we can add a symbol, and we can go search for our LMQ and grab our symbol, place it here. Now we will just fill out the schematic to match the reference schematic. So all the passives for this, for the most part, live inside the device library. And so we can just search here. We need to start with a resistor, so we can just grab a basic resistor. And then I'll add a capacitor as well, which will just be a C. And we'll need an inductor. So I like to place all these, and then I'll just duplicate them out as we need them. So at this point, we've matched the application schematic from the datasheet. I've gone ahead and added one extra resistor here, this R boot. The value of this resistor can be changed to change the switch node rise time in case we want to adjust that later. We'll start out with it at 0, but then we can play with different values to see if we can change the rise time and affect the EMI performance of the regulator. So just below the application schematic, they've got some example design requirements. These don't quite match our requirements, so we're not going to use them. They also have some typical external component values, and so these we can use to start filling in some of the values. So we're going to be shooting for a 2.1 megahertz switching frequency, and then we're going to have 5V out. We'll go through and check some of these values as we go through the table, but you can at least start by filling some of these in here. The first thing we need to check based on the switching frequency is, since the efficiency is related to the switching frequency, we need to make sure we'll stay within the thermal limits of the part. So they have on here some ambient temperature graphs versus the output current. And so we're not planning on operating this at 65 degrees C, so we're good to run at the 2.1 megahertz output switching frequency. The other piece is there's some limitations on these parts. There's minimums for how long the switch can be either on or off. And so if you want the part to operate in constant frequency operation, there's a couple equations that have to hold true. So we can go through and check this one where we have 5 volt out over Vn of max 2 and then times this T on. So we just need to make sure that our switching frequency stays within these bounds. As I go through this, I like to keep all of my math in Excel. So what we'll do here is we can start mapping out what these are. So we're going to have some parameters and values, and then so we're going to have our FSW. We want to be 100 kilohertz. Then we'll have our V out is 5 volts. Our V in will be nominal 24, but we could accept up to 30 volts in for this design. And then there's that T on min, and this we have to go look up elsewhere in the datasheet. So this will be up in the specification section. So the timing characteristics for this has the T on min here is the minimum high switch time. Gives some test conditions for that, but we can use this max of 70 nanoseconds. So then to make sure that we're within this, we're going to write out an equation that tells us what our switching frequency is here and make sure that we're less than that. So frequency max is going to be equal to V out divided by the V in max here times 70 nanoseconds. So we're going to have that times 1e to the -9th to turn that into nanoseconds. So that gives us hertz. We want this in kilohertz. So we're going to take this whole value and just divide it by 1000. So we can see that our Fmax here is 2.3 megahertz or 2300 kilohertz, and our chosen 2100 kilohertz is below that. So we meet that requirement. The next step here is we need to set the output voltage, and this is done through an output voltage divider right here. What the regulator tries to do is it wants to keep this feedback pin always at 1 volt for this particular regulator. So what we have to choose is a resistive divider that results in this being 1 volt when this reaches our output voltage that we want of 5 volts. Now they have a couple notes of that in here of that they recommend that the RFBT be 100 kilo ohms. So for that, we can choose actually match their example here. They recommend 100 kilo ohms for that, and then the other piece of the divider is 24.9 kilo ohms. Next, we need to work through the inductor value for the output inductor. This inductor acts as basically a filter to take the switching voltage on the switch node and turn it into a more constant voltage for the voltage output. They have kind of an example equation in here. We're using a pretty tight range, so we're going to use about 30% for our current ripple through the inductor. And so we can go through this. We'll put this equation into our spreadsheet. So I'll have L, and this equals V in, which we have listed here as 30 volts. Actually, we need to change this. That's our V in max. We also have a V in nominal of 24 volts. So for this guy, we're going to use our V in minus our V out. And then we're going to divide that by our frequency of switching, which since this is in kilohertz, we need to multiply by 1000 times K, which we're going to put right here. So that'll be 0. And then times our I out, which we're going to put right here. And that covers that. Then we multiply by the V out and divide by V in. And then we're going to get a divide by 0 because we need to put K here and I out. So our I out here we want to be 6 amps because that's the rated current for this regulator, and K is going to be 0.3. And so we get 1.05 e to the negative 6. So if we then take this and multiply it by multiply this by 1,000,000, then now we get this in microhenries. We need at least 1.047. We'll probably choose something slightly above that for this particular design. At this point, we're going to jump back to KiCad and start filling in some of the pieces for this. So we'll start filling in some of these values. So we can fill in, this top one was the 100k ohm resistor here. This guy is the 24.9 k ohm. Then we have our inductor, which we need to find a standard inductance value for this. So for our inductor, we're going to go with something from Coilcraft, and we're going to use one of their XAL ones. We're going to look at their XAL 40XX series. These are some shielded inductors. They're pretty small little surface mount parts. And we go down here and we had 1.04 that we needed, so we're going to go up to the 1.2 microhenry, and we just have to check and make sure that the saturation current is above the current that our max current that we're going to be using. So we're going to use this part, so we know that we need a 1.2 microhenry inductor on our schematic. So for that, we can take our inductor here and make this 1.2 microhenries. Now back at our data sheet, we want to select our output capacitors. We're going to select to meet the better transient performance from this. And so we're just going to grab, for a 5-volt output, we're just going to copy what they have here. So they're listing that we need 33 picofarad as our CFF, and we need 3 22 microfarad ceramic output capacitors. So we'll go add those to our board. So we did just have this one capacitor. We're going to move this over. So we're going to move this over and we're going to create 3 of them. So we need to duplicate this guy, so we'll have 3. And we're going to make each of these 22 microfarad capacitors as shown in the diagram. So these would be 22 UF. You can actually just edit this here. So that takes care of our output capacitors. Then the next piece this has us do is set this CFF capacitor. So that's this guy here. It says it needs to be a 33 picofarad. And it needs a 1 kilo ohm series resistor here. So this will be 1K. I'm going to clean these guys up since they're vertical to make them a little easier to see. The data sheet does talk about other ways to set this up. You can also use a combination of electrolytic and ceramic capacitors if you're trying to keep the cost of your ceramic capacitors down. On the input side, where we can go to next, which is up here, we need to make sure we have the right amount of capacitance there. So I've gone ahead and added an extra electrolytic capacitor here since we'll have long wires coming in here. We want to keep give us some extra capacitance here. The ones that will be close to the part, these two are supposed to be 100 nanofarads or 0.1 microfarads, and these will give us some bypass. These need to be placed as close to the part as possible. Basically what happens is when you turn this on, these two nodes, the VN1 and VN2, when the switch is going off, these are going to be powering that switch right there. And so we want to keep this current loop here very short on the input. And so it just needs a very small capacitance right there to deal with the high frequency component of the switching. Now here we need a little more capacitance, so we need a 10 microfarad bulk capacitance, and this will just need to be placed somewhere near this to help deal with some of the lower frequency components. TI recommends 2 different ways to do this. One is with this 0.1 microfarads, or one is with this bulk 10 microfarad here. The other way we can do that is just to duplicate this and have 2 of them and then use a slightly smaller value. So we're going to go ahead and do that. So these will actually be 4.7 microfarads. Looks like I missed hooking up the bias, so this just goes through here. Next, we're going to set the value of the C boot capacitor. This provides the voltage needed internally to turn on the switch. And so for this, TI just recommends using a 0.1 microfarad capacitor. It does need to be at least 10 volts, but that shouldn't be a problem there. And this resistor, we're going to start out with a 0 ohm one. This will just be a short. As we said, this changes the gate drive strengths so that we can reduce ringing if we need to later on when we're testing it. The VCC pin here, this is just a bypass cap for the internal regulator that powers the internal circuitry. This just needs to be a 1 microfarad cap. Since we're not using the low voltage lockout, we actually don't even need this resistor here, so we're just going to tie the enable pin high to the power input so that when we plug this in, it turns on. Finally, we need to set the switching frequency. So this is the RT resistor. They give both an equation for this, but we can also just look here and set the value based on this chart. It looks like for 2100 megahertz or 2100 kilohertz, we need to be at about 6 ohms on that resistor. So we'll go ahead and set this resistor to 6 ohms. So with that set, we now have the full schematic done here. So we can go ahead and save this. Next step we want to do is annotate this. So this goes and fills in all of the reference designators on the schematic. Now that those are filled in, the next step will be to assign footprints. So that's all for creating the schematic. In the next video, we will create and assign footprints and do the layout for this.